Welcome back, everyone, for another deep dive.
Yeah.
And today we're diving into something that I think is pretty cool.
Oh, yeah?
The Lorentz force.
Absolutely.
So we've got a resource here. It's an educational page.
Okay.
All about this 3D Java applet that was made to help students
Right.
learn about the Lorentz force.
Yep.
Yeah.
And you know what, though?
Yeah.
Even though it's for students, this concept is behind, like, so many technologies
Oh, totally.
we use every day.
Electric motors, even the Northern Lights.
The Northern Lights.
I mean, it's pretty amazing. So
Yeah, we're going to unpack a lot today.
yeah, I even heard something about a
Oh, yes.
hand rule.
The FBI.
The FBI hand rule.
Yeah.
Okay, well, we'll have to get to that.
We'll get to that.
But first,
Yeah, let's start with the basics.
Okay.
Like, imagine you have a charged particle, like an electron,
okay.
and it's moving through a magnetic field. The Lorentz force is that force that the magnetic field exerts
Okay.
on that moving charge.
So it has to be moving.
It has to be moving. That's key.
Okay.
A stationary charge
Yeah.
wouldn't experience any force.
Interesting.
But as soon as it starts moving,
Yeah.
it's like
Mm-hmm.
it encounters this invisible current
Okay.
that pushes it sideways. Yeah.
That's a good way to think about it.
Visualize it.
So what determines how strong that push is?
So there's a few
Yeah.
key factors that
Okay.
that our source material breaks down.
Yeah.
One is the current,
Okay.
which is basically how much charge is flowing.
Right.
Higher the current,
Yeah.
stronger the force.
Okay.
Like a river,
Uh-huh.
wider, faster river,
Yeah.
stronger current.
Okay.
Makes sense.
That makes sense.
What else?
What
The
else?
strength of the magnetic field
Okay. Yeah, of course.
itself
Yeah.
plays a role.
Right.
Stronger magnetic field,
Yeah.
more powerful force on that charge.
So if you have like a weak current
Yes,
and a weak magnetic field,
you got it.
it's going to be like a much weaker force
Much weaker.
than like a really strong current
Absolutely.
and a really strong magnetic field.
Yeah, and we can't forget about
Yeah.
the
The
length
length of the wire.
of the wire
Okay.
that's carrying the current
Uh-huh.
within the magnetic field.
Okay.
More wire exposed,
Yeah.
stronger the force.
So it sounds like
Yeah, it seems like
bigger is better.
the bigger the better
Right.
so far.
Is that always the case?
Well, not necessarily.
Okay.
There's one more
Oh.
really crucial factor.
Okay.
It's a big one.
Okay.
It's the angle
The angle.
between the direction of the current
Uh-huh.
and the magnetic field lines.
Mm.
This can really
Okay,
change
great.
things.
Yeah.
So imagine
Okay.
like a boat
A boat. Okay.
trying to cross a river.
Okay.
If it's moving directly against the current,
Yeah.
it's going to experience
in the most resistance.
the strongest resistance,
Yeah.
right?
Yeah.
But if it goes with the flow,
Yeah. No resistance.
there's no resistance.
Easy peasy.
Right.
Okay.
It's the same with the Lorentz force.
Okay.
If the current is flowing
Okay.
parallel to the magnetic field lines,
Yeah.
the force is zero.
Oh, wow. So there's no force.
There's no force
At all.
at all
If it's perfectly aligned.
if it's perfectly aligned.
Wow.
But when the current is perpendicular
Okay.
to the magnetic field lines,
Uh-huh.
that's when you get the max force.
Okay.
It's like our boat
Yeah.
trying to cross the river
Right.
at a 90-degree angle.
Okay. So it's like
Yeah.
a sliding scale.
It's like a sliding scale.
Zero.
Force when they're aligned.
Mm-hmm.
Max force
Perpendicular.
when they're perpendicular.
Okay.
Yeah.
That's a good analogy.
It is. And there's this neat trick that our source mentions to help visualize this relationship between the current magnetic field and the direction of the force.
Yeah.
It's called the FBI hand rule.
The FBI hand rule.
Yes.
Okay, now you're talking.
Now we're talking.
I was hoping we'd get to that.
Right.
So tell me, how does this work?
Okay, so picture this.
Okay.
You're going to extend your right hand,
Uh-huh.
thumb, index finger, middle finger,
Okay, got it.
all pointing out.
Okay, my hand's ready for physics.
All right, so
What do I do?
point your index finger straight ahead.
Okay.
That represents the direction
Okay.
of the magnetic field.
All right. B.
So B for magnetic field.
B for magnetic field.
Index finger, got it.
Okay, now point your thumb straight up.
Up, okay.
That's the direction of the force.
Of the magnetic force.
Magnetic force or F.
Okay, so index finger is B, thumb is F.
You got it.
What about my middle finger?
Your middle finger's going to be pointing out to the side.
Perpendicular to both your thumb and index finger.
Oh.
And that represents the direction of the current.
So
there you have it.
Wow.
FBM.
Hands like a cheat sheet.
I know, right?
For physics, this is awesome.
It's pretty cool.
So I can see how,
Yeah,
these three things are all related.
exactly. And the best part is
Yeah.
you can use this to predict the direction of the magnetic force.
Okay.
In any situation. So just orient your hand so that your index finger points along the magnetic field.
Okay.
Your middle finger along the current. Your thumb will automatically point
that's cool.
in the direction of the force.
So if I change the direction of the current, say I just flip my hand over.
You got it.
That's so cool.
It's all it takes.
Oh, yeah.
Yeah.
I like that.
It's a handy tool to help visualize.
I can see how this would be so helpful for students. You know, trying to understand this stuff.
To wrap their heads around it.
It's way easier to like actually picture it.
Absolutely.
Than just looking at a formula.
Yeah, and that's where this Java applet.
Right, the simulation comes in.
What can you actually do with it?
I know. So remember those factors we talked about earlier?
The strength of the field, the length of the wire, all that.
A current.
Yeah.
The magnetic field strength.
Yeah.
Length of the wire.
The
angle.
Yeah.
You can adjust all of those.
In the applet.
In the applet.
Get out.
And see how it affects the force in real time.
So you can really test out all those relationships.
That's exactly
what we're talking about.
Exactly. And you can change the angle.
Oh, wow.
Just like you were doing with your hand.
I love it.
To see how that impacts the force.
It all ties back.
It all ties together.
To the hand rule.
It's awesome.
This is so cool.
It's like having a little virtual lab.
Right in your computer.
So cool.
What else can you do?
Yeah, what else?
Well, the applet lets you actually see the wire move.
Oh, wow.
In response.
So it's not just like...
To the Lorentz force.
Yeah, it's not just like a diagram.
You can play and pause.
Oh, wow.
The simulation.
So cool.
Observe how the wire moves.
That's awesome.
As you tweak those variables.
So you can see like the data.
Yeah, you can even see graphs.
Wow.
That show things like the wire's position over time.
That's really cool.
It really highlights something important about the Lorentz force.
Okay, what's that?
It doesn't act in isolation.
Right, okay.
In the real world.
There's other stuff going on.
There's other forces at play.
Okay.
Like drag force.
Drag force.
Yeah, which the simulation also includes.
Okay, now, is a drag force like kind of like air resistant?
Exactly.
Right, yeah.
It's the force that opposes motion through a fluid.
So like a car moving through air?
Exactly. Yep. Or a boat moving through water.
Okay.
So
how does that play in with the Lorentz force?
So picture our wire
okay.
moving through the magnetic field as it moves.
Yeah.
It's also pushing against the air.
Right.
And that creates drag.
Okay.
Tries to slow it down. So the stronger that drag force is, the less the wire is going to be able to accelerate under the influence of that Lorentz force.
Oh, so it's like a push and pull.
It's a tug of war.
Kind of.
Exactly. And the applet lets you manipulate that drag to see how it affects
the wire's movement.
The wire's movement.
Oh, that's awesome.
Yeah, it's pretty cool.
So it's not just the basic Lorentz.
The basic concept. It shows how it interacts with other forces in a dynamic environment.
That's a good point.
That's why these simulations are so valuable for learning.
Yeah.
Because you can
you can actually see it.
You can see how it all
works
together.
That's really cool.
It makes you appreciate how much is going on behind the scenes.
Yeah. Even with
even in simple.
Yeah.
Seemingly simple phenomena.
Right.
It's actually quite complex.
Yeah.
When you think about all the forces at play.
And that brings us back.
To
why this is important.
So why this is important.
To understand.
The Lorentz force.
Yeah.
So it might seem simple on the surface.
Right.
But
it has so many applications.
It's got incredibly far-reaching applications.
Okay, well, tell me about some of those.
All right.
Okay, so we've talked about how the Lorentz force works and everything.
Yeah, we've even got our handy FBI rule.
Right, we can predict the direction.
Exactly.
So cool.
But how does this all connect to the real world?
Yeah, what's the point?
Well, you mentioned electric motors earlier.
Oh, yeah.
The Lorentz force is actually the driving force.
Really?
Behind how they work.
Okay.
So inside an electric motor, you've got these coils of wire that carry current.
Right.
And they're placed within a magnetic field. And the interaction between that current and the magnetic field generates a force that causes the coils to rotate.
Right.
Which then drives the motor.
So something as simple as...
I know, it's pretty amazing.
A wire and a magnetic field is what's powering,
It's pretty remarkable.
All these motors?
It is, and it doesn't stop there.
Oh, there's more.
There's more.
Okay.
Think about generators.
Okay.
They work in the opposite way to motors.
Oh.
So instead of using electricity to create motion, they use motion to generate electricity.
So it's like the same force.
The same force.
Just like in reverse.
Yeah, pretty much.
Wow.
Yeah, so you're starting to see how...
Yeah, the Lorentz force is like...
It's everywhere.
Everywhere.
And then there's also things like loudspeakers. You know, they use the Lorentz force to convert electrical signals into sound waves.
Oh, wow.
Yeah, so you have this coil of wire attached to a diaphragm.
Yeah.
Which is placed in a magnetic field.
Okay.
And when an electrical signal passes through that coil, it experiences a force.
Right.
Causing that diaphragm to vibrate.
So that's what's making...
Which produces the sound we hear.
The sound.
Exactly.
I never would have thought.
I know, right?
That's how speakers worked.
Yeah, so we've got motors, generators, speakers.
That's like all this everyday stuff.
All this everyday stuff.
Uses this one principle.
And we haven't even talked about some of the more advanced applications.
Okay, like what?
Like particle accelerators.
Oh, wow.
They use the Lorentz force to steer beams of charged particles.
Really?
Which leads to...
And they're literally steering.
They're steering particles.
Wow.
Which leads to all these groundbreaking discoveries.
So it's like at the heart of like cutting edge science.
Exactly. And even beyond that, the Lorentz force plays a role in some of the most beautiful natural phenomena.
Like what?
Remember the Northern Lights?
Yeah, the Northern Lights.
How does that work?
So they're created when charged particles from the sun collide with atoms in the Earth's atmosphere. These collisions excite the atoms.
Yeah.
Which makes them emit light.
Okay, so that's what's making the light.
That's what's making the light.
Okay.
But what guides those particles towards the poles?
Right.
You guessed it.
The Lorentz force.
The Lorentz force.
It's everywhere.
The Earth's magnetic field interacts with the particles and steers them towards those polar regions.
That's crazy.
So the same force
it's mind-blowing
that powers our electric motors
is
responsible for one of nature's most beautiful displays.
It really is amazing.
It's incredible. When you think about it like that,
it really highlights how interconnected
everything is.
The physical world is. It makes you wonder
what else?
What other applications are out there?
What else don't we know about?
Waiting to be discovered.
All right, well, I think this has been a really great deep dive.
I agree.
I learned a lot.
Yeah, me too.
The Lorentz force is a lot cooler.
It is pretty cool.
Than I thought it was.
Yeah. It's got a bad rap, I think.
It does.
For being kind of a dry physics concept.
Yeah.
But really,
it's everywhere.
It's all around us.
Yeah. So thanks for listening, everybody.
Thanks for joining us.
And we'll see you next time.
See you in the next deep dive.